Right, so under second order differential equations, first we will consider homogeneous differential equations. Homogeneous differential equation means if we have a second order differential equation. A second order differential equation means we have a second derivative term in this equation. So order of this differential equation is equal to 2. So we have a second derivative term. The coefficient of the second derivative is a. The coefficient of the first derivative is b, and the coefficient of the y term is equal to c, and you can see the right hand side is equal to 0. So when the right hand side of the equation is equal to 0, it is called a homogeneous differential equation. So we are going to look at the methods of solving homogeneous differential equations. So here, when we are solving these differential equations, we are going to replace these derivative terms using a D operator. So we use this symbol capital D to represent d by dx. That means the derivative of some function with respect to x. So the capital D is not just a symbol, it means the derivative. The first derivative. So d squared means it is the second derivative. So this is the second derivative of some function with respect to x. So we can write down this second order differential equation by replacing this second derivative and the first derivative using this d operator. So we can rewrite this as a d squared, because this is the second derivative. We have the second derivative here, plus b, the first derivative, plus the constant times y. Right, so d squared y means the second derivative of y, because d is d by dx. So d squared y means d squared y over dx squared. So the second derivative of the function y. So this is equal to 0. And this equation is said to be in D operator form when we replace the derivative terms by this capital D. And then when you are finding the solutions of the second differential equations, we assume that the solution for this second order differential equations takes this form. So this is simply an assumption, right? So this is an assumption that y equal A is a constant, EMX is a solution of the second order differential equation. So assuming that this is a solution, right, we can find the first derivative of this y with respect to x, that is differentiate this function. So a is a constant, this is an exponential function, so you know how to differentiate this exponential function. So m comes here, m is a constant, so am emx. Similarly, we can find the second derivative of this term. So the second derivative means, again, we are differentiating this exponential function, so we have another m term, so it becomes am squared emx. So now we can replace these values in the second order differential equation. The second derivative is am squared emx plus b, the first derivative is am emx, this one, plus c, y is a emx equals 0. So we can write down this equation taking aemx as a common term, taking outside the brackets as a common term. So we can write down this differential equation as am squared plus bm plus c. Right. So in the first place, we have assumed that y equal aemx is a solution. So if it is a solution, so when we say this is a solution, we assume that this is a non-zero solution to the differential equation. So if this is a non-zero solution, if this term is not equal to 0, for the right hand side to be equal to 0, this term here, this expression here, am squared plus bm plus c should be equal to 0. Right? So we can say y equal a emx is solution of the above differential equation. That is, it is a solution of this differential equation provided that this expression here is equal to 0. Right? This equation is satisfied only if this term is equal to 0, if this is not equal to 0. So here this am squared plus bm plus c equals 0 is called the auxiliary equation. So that is the term that we are using for this equation, auxiliary equation. And then when we are going to find the values of m by finding the solutions of this auxiliary equation. Right? So this is simply a quadratic equation. This is simply a quadratic equation. So we can find m either by factorizing this quadratic equation or using the quadratic formula. You can use any method to find the solutions. Our final objective is to find the solutions of this quadratic equation or the auxiliary equation and find a solution for a second order differential equation. So we know for a quadratic equation there are three types of solutions depending on the discriminant of the quadratic equation. So these a, b and c are real values, and then b squared minus 4ac is called the discriminant of the equation. So we know if the discriminant is positive, that means if b squared minus 4ac is positive, then we have two different real roots, right? And if b squared minus 4ac is equal to 0, then we have two equal roots, right? Two real equal roots. And if the discriminant or b squared minus 4ac is negative, then we have two complex roots. So there are three types of solutions for a quadratic equation. It can be either two real roots, two equal roots, or two complex roots. So the solutions for the second order differential equation depends on this type of solutions for this auxiliary equation. That is, if we have two real roots, we have one type of solution. If we have two equal roots, then we have another type of solution. And if we have two complex roots, we have another type of solution for the second differential equation. So this is the procedure to solve differential equations of this form. This form means a homogeneous second order differential equation. First step is you have to rewrite the second order differential equation using the d operator, and then substitute this d by m, and then we find the auxiliary equation in the form of m. Auxiliary equation means when we replace this d operator by m, and then we are looking for solutions of this quadratic equation in the form of m. So this is a quadratic equation. So if we can find the solutions for m, then if the roots of the auxiliary equation are real and different, that means the discriminant is positive. So we can say one root is equal to alpha and the other root is equal to beta. Then the general solution takes this form, right? So you should know these 3 points, that is, the points should be given that if the roots are real and different, the solution for this auxiliary equation is y equal a e alpha x. So this is alpha means one root plus b e beta x. So here we have the roots in the exponent. A and b are constants. So if the roots are real and equal, that means we have only one root. We have two roots, but those two are equal, so we have only one value. sorry, not one root, one value. So say it's equal to alpha, then m is equal to alpha, then the general solution takes this form: y equal ax plus b times e alpha x. So alpha is the solution for the auxiliary equation. And if the roots are complex, that is m equal alpha plus jb or alpha minus jb. So here the two roots are the conjugate of each other. That means we have a difference in sign here before the imaginary part. Then the general solution takes this form: y equal e alpha x, that is the real part of this complex root, a cos beta x. So beta means the imaginary part of the complex root, plus b sine beta x, right? Then if we are given some boundary conditions, we can determine these constants a and b. If not, you can't determine the constant values a and b. You can find only these alpha and beta values from the auxiliary equation. So if we have the solution in this a and b form, it is called the general solution for the differential equation. But if the conditions are given, if we have some boundary conditions, then we can determine the constants a and b, so that it is called the particular integral of the differential equation.